Okay, as I mentioned previously, um, the purpose of this final tutorial video is to give you 4 commonly used inferential statistics. The 4 most commonly used inferential statistics are independent samples t-test, one-way ANOVA, correlation, and chi-square. And just to give you a little bit of a flavor of when you would use what, let me introduce them. An independent samples t-test is used when you have 2 groups or 2 levels of an independent variable and they're distinct categories. For example, if I wanted to compare males versus females, in this context, a person would identify or report that they identify as one or the other, right? And if I gave more options, it would identify as whatever. But in this case, we're going to use males versus females, 2 separate categories, right? So now, what happens when your independent variable has more than 2 levels? So 3+ levels, for example, ethnic categories, right? Or university status, freshman, sophomore, junior, senior, etc., or grad student. Now you have more than 2 categories. You're going to want to use a one-way ANOVA because it allows you to run a comparison of every pairwise group while maintaining the same level of significance or an alpha of 0.05. So again, independent samples t-test, your independent variable has 2 levels or 2 categories. Your dependent variable is interval ratio, or in SPSS it would be called scale. And then with a one-way ANOVA, your independent variable has 3 or more levels, and your dependent variables interval ratio or scale in SPSS. Now, I mentioned correlation. In a correlation, in order to use a correlation, you have to take 2 factors that are both interval ratio. Cannot be categorical data, so they have to be on a spectrum, both of them. So they both have to be numerical. And then we talked about a chi-square. So chi-square looks at whether or not their observed frequency is significantly different than what you might expect by chance, right? But a chi-square, we're looking at categories, which is typically nominal data. Now, technically, you can do a chi-square for 2 variables, which is nominal by ordinal, and I'll show you that when I get there. So these are the 4 most commonly used statistics, but time to show you how to do it in SPSS. So now, what I'm going to do is I'm going to go to Analyze tab. Analyze tab is going to be the most frequently used tab for SPSS. So you want to know where that is. So let me just make sure that I'm not highlighting anything. All right, whatever. It's going to keep highlighting. So Analyze. Now we talked about in our first video, our second video, Descriptive Statistics. Now we're going to go to Compare Means. Now, you'll see the blue highlighting on Analyze Compare Means. It's going to give you a drop-down menu. What's cool about this is I said that the independent samples t-test is the most commonly used t-test, but you do have other options like a one-sample t-test. That's when you're comparing your sample relative to a population, and you know the population mean and standard deviation. And then we have paired samples, or what's sometimes called matched pairs, or dependent samples t-test, and so forth. But most of the time you're comparing distinct groups. So let's go across, compare means, independent samples t-test. Now I say, gee, I wonder if males and females differ on, I don't know, depression, right? Because if you look in abnormal psychology, typically females have higher rates of depression, or they report higher rates of depression than males. Let's see in my sample if that was the case. So I'm going to go down and I'm going to find gender. Now, I highlight it. Now, the grouping variable is analogous to your independent variable. When I press the arrow on the bottom, it's going to say, well, what groups? Because, again, a t-test, you're comparing two groups. You may have more than two levels of a given independent variable. So you may have to specify it. So you'll notice I brought the gender over and it has question marks. So I'm going to call 1 and 2 because I named male and female 1 and 2. So I'm going to click Define Groups, and for group 1, I'm going to call it Category 1. For group 2, I'm going to call it Category 2. And then I said, gee, I want to know if males and females differ on depression. So the PHQ stands for the Patient Health Questionnaire, which is a measure of depression. And I'm going to do a PHQ total. So I'm going to click that, put that into my test variable. Test variable is analogous to your dependent variable. You'll notice that the dependent variable has to be interval ratio, and that is a ruler. That is a ruler format. So we have males and females, independent variable, and the dependent variable is scale. So I'm going to click OK, and it's going to give me an output. Now, when I take you through this output, you're going to have descriptive statistics and inferential statistics. Your professor will teach you how to write up your results section. I usually give my students a template on how to write results. But in this sample, we have 384 males, 683 females. Now, as I mentioned in a previous video, the group that we were looking at were psychology students, so it should not shock you that there are more females than males. The mean PHQ total for males was 5.97. The mean PHQ total for females was 6.42, and there are standard deviations. Now, if you eyeball this, the descriptive statistics, we know that females have higher mean scores for depression. But do we have significant differences in these mean scores? For that, we have to use an independent samples t-test. Now, the independent samples t-test, I'm going to take you through the different parts because there are various assumptions of an independent samples t-test. One assumption is that you have distinct groups, that there's independence, so the people identified as male are separate from female. We have that. Another assumption is that we have a normal distribution, right? So that we have a normative sample. So we want to test for equality of variances or homogeneity of variances. And then the third thing is equality of means. So we'll go through that. So if we look at the Levine's test, this is testing the assumption of equality of variances. So this first sig, which is 0.144, is considered statistically non-significant. So that's a good thing, actually. In order for something to be statistically significant, the standard alpha is 0.05 or lower. Here we have 0.144. So we assume equality of variances. Why? Because this sig value is not 0.05 or lower. Now, in order to determine whether these means, which my cursor is circling around, are significantly different, well, that's what the t-test does. So if we go to the second sig, we get a 0.187. And 0.187 is also greater than 0.05. And as such, in this particular sample, we found no statistically significant differences in depression scores between males and females. Now keep in mind, this is a non-clinical sample. This is a college sample. So this may not shock you all that much because we deal with relatively healthy young adults. So it may not manifest. If this were a clinical population, it would look very different potentially. Okay, so that's our independent samples t-test. Another example might be alcohol use. Let's see if across levels of college, there are significant differences in alcohol use. So I'm going to minimize the output, and I'm going to go into my variable view to find my groups. So I called levels of college, freshman, sophomore, junior, senior, and other. Other were grad students. And these were the categories, right? So let's see if alcohol use differs significantly across these distinct levels of college. By the way, sophomore is misspelled, but that's a separate issue. We would expect there to be significant differences because typically the age goes up, right? Now, but because we have 1, 2, 3, 4, 5 different groups, we can't do a t-test, because if we ran t-tests for all of these, the risk of making a type 1 error, that is to say, finding significant differences between the groups by accident, would increase, right? So we're going to do a one-way ANOVA. So this is the second statistical test. So for this, we're going to do analyze, compare means, one-way ANOVA. Now, the independent variable is called factor in this one box. So we're going to find college, which were our 5 groups. Let's scroll down, find college. We're going to put that in there as factor. That's our independent variable. And then we're going to find alcohol use, which I called the DAN6. And we're going to do post hoc comparison. Now, it's very important that if you find a significant model, in order to determine which groups differ from one another, you have to do a post hoc analysis. Now, there are different ones. Many people use Tukey. Many people use LSD. I like to use the Sheffy. The Sheffy is more conservative, so it's harder to reject the null. So I'm going to click that as my post hoc. And then we also have options. Now, I like to have my descriptive statistics. I like to have my mean plots to see what it looks like. So I'm going to click those, click continue, and click OK. Now, my second analysis that I ran is a one-way ANOVA. Now, because I asked for the descriptive statistics, you will get the frequency of each group. You will get their mean. You will get their standard deviation. You will get their standard error, their confidence interval, and the range of scores. And then you will get the ANOVA. Now, when I teach statistics, I actually have them do this by hand, but it takes a decent amount of time to do this. And certainly with 1,000 participants, you probably wouldn't want to do that by hand. So it spits out a model for you. So just to take you through the model, you have between groups variance, within groups variance, and total variance. Between groups, that is to say, between one category and the next, how much of the variability is due to true differences versus error. Within groups variance, within groups is how much you vary within yourself. Now, typically when we talk about between groups variance, Jacob Cohen, a statistician from NYU, he talks about between groups variance as looking at true differences and error, right? Because you still could have error between groups, but most of it is actually real or meaningful differences, whereas within groups is routinely error. Then we have our sum of squares, degrees of freedom. Degrees of freedom between groups, that's formulaically k minus 1, or the number of groups minus 1. So I know I have 5 groups because it says 4, right? And again, we went through it: freshman, sophomore, junior, senior, and other. Those were our 5. Now, within groups, degrees of freedom, that's n total minus k. So that would be 1,066 minus 5 gives me 1,061. You add these up, you get 1,065. All right, now to get mean squares, all we do is take this number divided by this number gives you this. Same thing, this number divided by this number gives you this. Now SPSS does this all for you, but just to show you. And then if you divide mean squares between groups by mean squares within groups, you get the F value. But now, The total general model, I got a 7.718 for the ANOVA. And the question is this F value statistically significant? Well, we go to the SIG column and it says 0.000. That is to say, the probability of this F value occurring by chance is 0.000. Now, it's not no chance, but because SPSS routinely reports SIG as in 3 decimals, what I would say is P is less than 0.001. So we do have statistically significant differences in alcohol use across the levels of college experience. Now the question is, we have a significant ANOVA, right? You see that SIG, 0.000. That is less than 0.05, so it's statistically significant. Now, which group differs statistically from the other? If you look at the general model, you couldn't tell. The only way to know which group differs significantly from the other is what we call post hoc analysis. Post hoc is after the fact, in which we look at the pairwise comparisons. Just a pro tip, if you have a non-significant ANOVA, if this SIG is greater than 0.05, don't even analyze the post hoc. Now, you won't know whether you have statistically significant differences beforehand, so when you're going through those click boxes, click the post hoc anyway, but if this general model is statistically non-significant, don't interpret post hoc. So we do, fortunate for us, have a statistically significant general model for the ANOVA. So I want to know, well, which group drinks alcohol more frequently than the other? So I'm going to compare my freshmen to the other groups. And what I find is if I go to the mean differences, you'll see there are little stars. Anything with a little star in the mean difference tells you that that is a statistically significant pairwise comparison. So freshmen versus seniors, there are significant differences in drinking habits, and freshmen versus other, which I said were grad students, significantly different drinking habits, right? Now, if you see a mean difference that's negative, that is to say that the first group has less drinking than the second group, which kind of makes sense, that seniors and grad students are going to drink more than freshmen, not because freshmen don't party, but it's easier to gain access to alcohol, particularly when you become 21. Kind of makes sense. And then we compare our sophomore versus senior, again, makes sense. And then when we get to juniors, there are no statistically significant differences. So juniors are interesting that they don't differ significantly from freshmen, sophomore, seniors, and others. So they're right on that cusp between becoming legal drinkers. And then going back to our seniors, they differ significantly from freshmen and sophomores with drinking more. And then our grad students drink more than freshmen. Now, if you have a hard time reading these mean differences tables, no problem. What we get here with our post hoc is the number of participants and their scores, right? So on that item on the Dan scale, the average for freshmen was 2.44, sophomore was 2.67, junior was 2.93, senior was 3.52, and other being grad students was 3.54. So you'll notice as you go, it goes up. Now the other cool thing about the Sheffy is it loads it. It's what this tells you is that according to this model, freshmen, sophomore, and juniors are in one group, whereas sophomore, juniors, and seniors get put in another group. Now there is some overlap, but that's because it's possible for a group like juniors to be in both categories. But here's a mean plot, and you'll notice that as they go through their college experience, the frequency by which they report using alcohol in the last 12 months goes up, which actually is not shocking. All right, so that is an ANOVA. Okay, the next thing you want to use is a correlation. Now, there are many different correlations, but typically, we're going to use pairwise correlations or bivariate correlations. rather than a regression because we're not trying to predict an outcome. We're just looking whether variables are associated. Going back to abnormal psychology, we expect things like anxiety and depression to be related. In fact, the likelihood of developing depression for people with anxiety is increased actually, and vice versa within a decade of a diagnosis. So let's say we wanted to do some comparison of the mental health factors. And I'm going to do a correlation between substance use, anxiety, and depression. So I'm going to do analyze, go to correlate. Now I'm going to do bivariate correlation. So it's just looking at the scores of one variable and the other. Again, these are not categorical variables. These have to be scale variables. So I go to bivariate, pops it open, and I'm going to do the Dan total, right? That's adding up all the substance use in the last 12 months. I'm going to do the PHQ total, which is scores on depression scale, patient health questionnaire, and the GAD, generalized anxiety disorder scale, GAD-7, total scores. Now you'll notice all of these are scales, so we can run a correlation. And what I'm going to do is I'm going to do means and standard deviation because it's helpful when you're reporting your results. I'm going to click OK, and here we have it. So now we have our total scores on each, standard deviation, and now if we look at it, this total score refers to Dan total or substance use total scores, right? And we're correlating that with depression and we're correlating that with anxiety. Now, what we find is a positive correlation between substance use and depression. Now, how do I know it's positive? Because there's no negative here. So it's 0.254. Now, this is considered a weak correlation, but just because it's a weak correlation doesn't mean it's not statistically significant. So you'll see those little stars there. Now I know I have a statistically significant difference, but what is the actual probability of getting this result by chance? 0.000. So this correlation, the relationship between substance use and depression, the likelihood of getting that by chance, P is less than 0.001. Same thing with anxiety. Substance use and anxiety, positive correlation, 0.266. It's a little bit stronger than the depression one. And we have 0.000, so there's a significant relationship between substance use and anxiety. Positive. Weak correlation, but statistically significant. Now, this should not shock you because there are different theories as to why people use substances, right? And based on the research, people use hallucinogens different than stimulants and depressants. In fact, there's a theory that it is used to mask an existing problem where hallucinogens might be used for mind expansion, but that's beyond this mini lecture. But in general, if I took all substances, stimulants, depressants, and so forth, we would expect there to be a positive relationship, which we found. Now, the last relationship that we're going to look at is anxiety and depression, which is how I started. Here we have a 0.76 correlation. That is a very strong correlation. 0.76 is a strong correlation, and that's consistent with past research. Now, the probability of getting a positive correlation of 0.76 by chance is P is less than 0.001 because you see the 0.000 again. So look, we know that substance use is linked to anxiety and depression, but the strongest correlation that we have out of the whole mix is anxiety related to depression. So as anxiety scores increase, so do depression scores and vice versa. All right, so that's a correlation. The last example that I'm going to use, and I'm going to use it what is called a chi-square for independence. Now the chi-square is kind of hidden, to be honest with you. If I wanted to know whether there was a relationship between two or more categorical variables, I would use the chi-square for independence. Now let me go into my data file and see what category we have. Gee, I wonder if there's a relationship between gender and ethnicity. Now, no, gender and college status. I don't have a reason to pick those two, but what the heck. Let's do analyze, descriptives, crosstabs. Now it's interesting. I said we're doing a chi-square, but here I am talking to you about crosstabs. Well, in the crosstabs, you can find the chi-square. So I said I'm looking for the relationship between gender, which is a categorical variable, and college status, freshman, sophomore, junior, senior, and other. So now I put my variables in there, and then I click statistics. And you'll notice that hidden within the crosstab statistics is chi-square. Now I did say that you can run nominal statistics relative to interval statistics and so forth, but the one we're going to use is a regular chi-square. Click continue, and I run that model. What's nice, we get our chi-square, we get the outcomes, we get our descriptive statistics, the number of freshmen that are male, sophomore, junior, senior, and so forth. And then we get our Pearson chi-square with 8 degrees of freedom is 0.023. So using a chi-square for independence, we found a significant relationship, because if it was non-significant, they would be independent. But if we find a statistically significant Pearson chi-square, then we know that they are related actually. So here we find gender is related to college status. And these are your 4 basic statistical outputs that people commonly use. Again, there's much more sophisticated factorial ANOVAs, repeated measures ANOVAs, regression analyses, but in an introductory experimental class, I can't imagine that you're going to need more than that. Okay, so let's stop here.